across the World Wide Web, on your mobile devices, on social media platforms. This is Jambo Radio! www.jamboradio.co.uk. We are multilingual. We are conversational in the languages you best understand. We are Jambo Radio! Jambo Radio, inspiring transformation.
Well, hello, and welcome to another exhilarating episode of the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. Today, we're going to be plunging into the vast ocean of knowledge, and we'll be dissecting the electrifying details and marvels of STEM, science, technology, engineering, and mathematics. So today we're going to be setting off on a journey into the intriguing and ever-evolving universe of electronics and semiconductors. And on today's show, we'll be delving into a thought-provoking topic. Can high-frequency electronics shape our future? So we have an expert in the studio, of course, as usual, who will be helping us with the answer to that question. And yes, you could say the question of the week is, how will next generation semiconductors transform our world? So we're going to see the answer to that as well. Well, I'm your host, Dr. Adetunmise Dada. And don't forget, you can tune in to the show via DAB, and you can catch us live and in video at jamboradio.co.uk. We also encourage you to subscribe to Jambo Radio Scotland channel on YouTube, as well as all our social media handles. So, with that, what are we going to be enjoying today? What will we be covering today? As usual, we're going to start with some science news highlights, and then we will interview our guest. And our guest, as hinted at earlier, is an electronics visionary, and more on that will come later. Of course, if you'd like to join in the conversation, you'll be able to do that through the website, and we invite you to do that very much. We'll have another round of the interview, which will focus on the science question for the week. And then afterwards, we'll enjoy some jokes, some science electronics themed jokes. So that's something you wouldn't want to miss. So please stay tuned, don't go anywhere, and keep that dial locked in on Jambo Radio. So let's dive in. Good. So let's have a quick introduction of our guest in the studio today. Today we have the privilege of hosting in our studio Professor Edward Wasige. And it is my pleasure indeed to welcome you, Professor Wasige. How are you doing today?
Thank you very much. Thank you for inviting me to this show. Yeah, I very much look forward to sharing and discussing high-frequency electronics and how the future may look like.
Thank you very much. That's fantastic. I really look forward to that as well. Of course, Professor Wasige is a visionary, as said, in the realm of high-frequency electronics, and he's someone you could call a beacon of innovation in electronic and nanoscale engineering. He has dedicated his career to advancing the frontiers of knowledge in this area when it comes to electrical engineering, electronics engineering, and that spans from the intricacies of microelectronics to the vast potential of telecommunications. So it's my great honor to welcome Professor Wasige today. Presently, Professor Wasige is at the University of Glasgow, and he leads the high-frequency electronics group within the Division of Electronics and Nanoscale Engineering at the University of Glasgow. He is known for his pioneering contributions to compound semiconductor electronics, and this involves work on the wonders of gallium nitride device technologies, for example, for power and microwave electronics, as well as indium phosphide-based devices for microwave and terahertz applications. And we see Professor Wasige has behind him, and currently an illustrious academic journey that spans continents. He's been from the University of Nairobi to the prestigious institutions in Germany, as well as Israel, the United Kingdom now. And of course, we can say Professor Wasige is a torch bearer when it comes to the world of high frequency technology. So also good to mention is that he has been decorated with various distinctions, and his expertise is also solidified by his affiliation with eminent engineering societies. So you can be sure that this discussion promises to be an exciting and very informative one. Fantastic. So we'll discuss more, and we'll open up our discussion more after our science news highlights. So coming now to our science news highlights. Well, we have a few headlines today. Today we've chosen headlines that are a little bit aligned with our topic of electronics and semiconductors and so on. So the first highlight that kind of caught my eye in the press recently was this one about a brainy transistor. So it's called a synaptic transistor, and it's been said to open new horizons for brain-like computing. Now, what's really special about this transistor? The interesting thing about it is the fact that it not only is able to process information, but also stores information. And in fact, in a groundbreaking study published in Nature, a team of researchers from Northwestern University, Boston College, and MIT unveiled this state-of-the-art synaptic transistor. Of course, the synaptic comes from, the connection with its similarity with how the brain cells work. So synapses. So synaptic transistor, it mirrors its ability to perform higher level thinking and processing of information. Now, what sets it apart is that unlike previous models, which required cryogenic conditions, so cooling it down to really, really cold temperatures and using all, very complicated equipment to do that, this innovative device operates effectively at room temperature, very much like our brains, you could say. And that marks a leap forward in neuromorphic computing. Now, this transistor stands out for its dual capability to process and store information concurrently. Now, apparently that's a feat that promises to revolutionize artificial intelligence, that's AI, that we all know about, and machine learning and so on. Now, the other thing about this transistor is that it consumes very, very little amount of energy, and it's really, really fast. And so it's poised to tackle the increasing demands of data-intensive tasks with AI and other related fields. And it will do that without the high power costs associated with traditional digital computing. So this is a very exciting development indeed. So that's some new results coming from MIT on electronics. Another headline that I would like to highlight is on 3D printed electromagnets. This is really, really exciting as well. So 3D printing of devices as complicated as electromagnets. Now, just this month of February 2024, engineers have achieved a milestone in 3D printing, and in the form of 3D printing of electromagnets. And electromagnets are at the heart of many electronics. So this innovation indeed could revolutionize how we manufacture everything from dialysis machines to speakers, and this will make it much simpler and much more cost effective to manufacture these devices. So you could say the future is printing. So 3D printing is making its way even into manufacturing of electronics. So please check out this news at news.mit.edu, and you can read about the MIT engineers 3D print the electromagnets at the heart of many electronics. Now, the third highlight that I would like to share is another very interesting one, again from MIT, harvesting energy with self-powered sensors. Yes, MIT researchers have designed a self-powered sensor that harvests magnetic energy. Just imagine that. That was published again last month in 2024, so January. Now, imagine being able to deploy sensors anywhere, say, for example, to the surface of Mars or to the farthest planets, without ever worrying about the need to change batteries or to do any such complicated task like that. So these sensors are able to harvest them. This is really, really exciting, and you could say a big win for remote monitoring and Internet of Things. So you can also uncover the details about that story from MIT, the news website from MIT. And with that, we'll wrap up the Electronic Innovations Digest, you could say, for today, our science news highlights. And each of these developments not only showcases the brilliance of modern science and technology, but also hints at the future where technology seamlessly integrates even more into every aspect of our lives, making it smarter, more efficient, and most importantly, sustainable. So let's stay curious and stay innovative and keep tuned in to our show for today. So very good. Now we're going to start our interview with our guest, Professor Edward Wasige. And once again, Professor Wasige, it is a great pleasure to have you with us in the studio today. It's an honor to have you with us. So what we're going to do is we're going to try to get to know you a little bit with this aspect of the interview. So we'd like you to share with us, for example, what initially sparked your interest in electrical engineering and high frequency electronics. We know that your journey from Nairobi to leading the group at the University of Glasgow in high frequency is something that's really inspiring. So we think there's one or two things we can glean or learn from knowing what inspired you to develop that interest.
Yeah, thanks very much. Yeah, I was born in Kenya many years ago, and when I went to high school, many people, many of my classmates struggled with the sciences and mathematics, and I was intrigued as to why. So I had a keen interest in the sciences, just because many people seem to struggle with this, and I really wanted to find out why. And after high school, after secondary school, I joined high school, and so my interest in the science developed even further, and so I chose to do engineering at university. So I studied electrical engineering at the University of Nairobi, and thereafter I came for my postgraduate studies, actually MSc in Liverpool, and PhD I did in Germany, then postdoc. And so why this area? Why initially it was really my surroundings, my peers, a good number of them who were not quite comfortable with the mathematics and the sciences, and just the curiosity as to why this was so. And I was able to develop competence in this, and eventually, I've had a career in this area, and I lead a group on high frequency.
Fantastic. That's really inspiring indeed. And how would you say these diverse international experiences have influenced your approach to research and teaching? For some people, it's not been the case. Maybe they've been in Glasgow, did their undergrad in Glasgow, did their sort of master's, PhD in Glasgow, and they're still here. How would you say just being exposed to different cultures from Africa to Europe and now in the UK, how would you say that's kind of shaped how you do things in your career?
My journey, part of it is by necessity.
Yes.
Yeah, so I was keen to be a university professor at an early age, and I was very interested in research, just to be able to shape the future of technologies. And so being born in Kenya after the undergrad degree, the research environment back home is probably not so well developed, and that's why I relocated to Europe for further studies. And the different cultures. So back home in Kenya, for example, the up to undergraduate level, it's extremely strong. So we were really good at maths and the basics of physics. But we didn't have the opportunity to do research. In Germany, during my PhD study, they have this phrase "made in Germany," engineering made in Germany. something along those lines. So they have a culture of doing things thoroughly. Actually, there's a German phrase which translates to doing things thoroughly. And my 1 year in Israel as a postdoc exposed me to yet another different type of culture. And so then Glasgow has been a good home for me because it provided me with the infrastructure and the funding to be able to realize dreams in terms of advancing modern technology, in particular in the high-frequency electronics area.
That's wonderful. Thanks for sharing that with us. I've heard about the German work ethic indeed, and yeah, that must have been really good as well. Great, fantastic. So, of course, you've been at it's a real privilege, I must say, to be at the forefront of developing such cutting-edge technologies, and from gallium nitride devices to terahertz electronics and so on. So, would you be able to share with us perhaps a discovery, perhaps a project that you're particularly proud of, and that how has that project or that result impacted the field?
Yeah, so over the years we've done various things, but probably I'll start by sharing about a little project that is related to one of the highlights of today. So neuromorphic computing. You just talked about the Snaptrick transistor by MIT. So from 2022 we had a FET open project. This is a Horizon Europe funded project.
I see.
Where we were developing semiconductors that would be used in neuromorphic computing. And as ever with research, the goals and challenges are roughly the same. The goals in that, so in neuromorphic computing in general, you want a system that will be able, for example, face recognition. If I look at you, I see that's Dr. Dada. It takes me no time to know it's you once we've met. But if we pass this through, and how much energy it takes for me to do that is almost zero. But the artificial systems that we develop that do facial recognition, they take maybe 100, 1,000 times more energy to do the recognition. So they take huge resources to do that. And so we had a new project called Chip AI. And so we developed so transistors at the heart of most electronics. But the primary to a transistor is a device called a diode, which you're familiar with. And we developed, based on a special diode called a resonant tunneling diode, we developed this device that is both sensitive to normal electrical signals, but it's also sensitive to light, and therefore it can enable to do and the neuromorphic computing, why it reduces energy requirements and does this at a fast level is that one is able to combine both the storage of the information you have and the processing. So the traditional computing systems, the storage is in one place and the computing is done on a different unit, and you have to shuffle information to and fro to be able to determine what it is. But the vision is that if you do this the way biological systems do it, so the way the brain does it, so you do this with one device. And so that's one interesting recent result that we've done. So neuromorphic computing is not quite my area, but we had a major EU project, and on the basis of this we are developing further programs of research to be able to reach to prototypes and hopefully products in the future. Probably I can talk a bit more about my own research, which I've done over the years, high frequency electronics.
We will come into that. But I just thought it's really, really exciting to see the direction things seem to be going. With regard to AI, being more resource hungry, but the other side of it, the technology that kind of carries that is becoming more and more capable as well to deal with the
indeed.
That's really fantastic. Also, I wanted to ask. So there are some of the obviously terminology that we've talked about. Yes. Just to break it down for some of our listeners, maybe who don't have the same background.
Yes.
And I know you can explain this much better than I could ever do.
Just ask the question. Let's give it a go.
So, for example, how would you, to a non-specialist, how would you describe what a transistor is, or to who the average person who doesn't is not into science at all?
Yes, so every person probably have a mobile phone in their hand, or they have a laptop, or have seen that. At the heart of this is the transistors, billions of transistors. What's a transistor? In its very basic form, it's just a switch. So you have electricity, and you can connect it. So if you have electricity, you can be able, with the switch, you can either turn it on or off, the way the switch on the wall you have at home. So the transistor is that basic device that can either turn it off or turn it on. And at the heart of the processing, we have many of these switches, and if you connect them properly, they're able to do logic. So, so sensors combined with logic from many transistors connected in an appropriate way, they do computation.
Yeah.
So computation essentially is transistors operating as switches. Switches just exactly as the switch on the wall. Yeah, but this is a semiconductor, a tiny piece of material which on it's able either to establish a link or disconnect a link, and by doing that, all the computation that we know today that we have can be done that way. And over the last, since the early 60s up to today, the number of switches we can put on the chip, the higher the number of switches, the higher the functionality. And today's devices, because we have so many switches integrated on chip, we can be able to do a lot of functionality. So that's one aspect, which is called digital.
Yes.
Then the other aspect of the transistor, depending on how much battery voltage or the level, how you set it up, it acts as an amplifier. We are all familiar with the amplifiers when we speak into the microphone.
Yes.
So we are familiar with you speak softly, but your voice can come out much more amplified.
Yes.
So transistors, other than doing the switching function, they can also do the amplification function. And how it does this is quite simple, but so you come in with your voice at a low level, or you collect a signal at a low level.
Yep.
And what is amplification? Through the transistor acting as a switch, it has a third. So as a basic switch, it switches between two main terminals.
Yes.
But when you add a third terminal, which is called the control terminal, or technically it's called the gate.
Yes.
And you bring your voice through the control signal.
Yeah.
Between the main terminals, this can be amplified. And so the transistor is so important in that it does switching, which enables us to do all manner of computation. And it can also enable us to amplify signals. So if we pick up signals that are at a low level, we can raise them up, or we do what's the technical signal conditioning. We can bring it to a level such that we can process it properly. So many words to say this, but
no, it's really fantastic. Your explanation is really helpful. I'm sure our viewers and listeners would really appreciate that. So it's if there's one thing to take away from this show, that explanation of what a transistor is, and how it can be used at the most basic level, I think is really nice. Thank you very much for sharing that with us. And now we know, from the Apple Pencil to the headphones to the mobile phones, so many devices have these tiny switches in them, which come together, and it's in large numbers, so many of them, to perform all the computation we see, whether that be, sending an email, or
Indeed.
Looking at a picture and modifying a picture.
Indeed.
So everything can be broken down into zeros and ones.
Indeed.
And these transistors are the little switches that do at the most basic level, the computation is really fantastic. Thanks for that.
Indeed.
So the other question I wanted to ask is, what advice would you give to young researchers, or perhaps people who are trying to walk in the path that you've been walking, and what would you like to tell them when it comes to acquiring funding, securing funding, and managing large-scale research projects?
Yeah, so I'll probably start with a more general answer. So my group over the last few years, just actually in January, we hosted a group of students from Eastwood High at the university, and they did a work placement program. During this program, they built Christmas lights, and so as part of the STEM program or outreach program of our research, we reach out to school pupils so that they come and see our research facilities. They build Christmas lights is what they do, and they visit our non-fabrication facilities. For young academics, and how to get research funding and develop the group, really it's the vision. It's the vision. I know you yourself. You're an academic and have a pretty good vision. So yeah. So it's the vision, and the vision is related to what are the challenges in society.
Yeah.
So for my own research, so I've been in Glasgow for the last 20 years. I joined in 2002. So I've been there over just 20 years. And research, the bulk of it has been to develop devices for next generation communication. Good. In Glasgow, in the last few years, there's been fiber broadband.
Yes.
And but our devices, they need a wireless connection. So developing devices which can interface with the lots of data that is possible through fiber broadband, so the wireless interface, so the devices which are able to do this is what I've been doing. And so to put together a research group and to have the vision and to win the funding to be able to realize this vision, there's several, at least 2-3 aspects to it. The first one is actual teaching, which is related to supporting PhD students.
Yes.
So recruitment of people with an interest in your research area, and offering supervision, helping them identify or share, be clear about the research challenge, and really supervising their work in terms of advice, or this has already been done, or guiding them to identify the problems and solving. So recruitment of PhD students is crucial. Why is it crucial? Because the way funding works is you only ever win research funding because it's public money.
Yes.
And why should they give it to you rather than somebody else?
Exactly.
So the way the choice is made is you have to show your track record. And one of the most important parts of the track record is just you quoted the recent publications in your research highlights. So I might have published this, and another university have done this. So with your team of PhD students, really a good PhD students, probably they publish 2-3 big results because you identified an important challenge for society. They spent 3 years working on it, and they discovered this is promising, or they even achieved. So when you publish this in a good journal paper and you apply for funding, say, look, we've done this, we know what the problem is, we can see the potential to impact a major area in society, surely you get money for it. That's and you're given money, and with the money you support more PhD students. And actually, with the money, you're able to recruit more advanced researchers. So researchers who already have a PhD, and they need maybe stay a few more years in research to develop
build
more.
there,
Yeah, indeed. So with the funding, you have an even bigger and more competent team. And you do more, and then it goes on like that. And actually, as new problems, or you find another interest. You find another interest, and you develop. Many of us will have a primary research area, but we would also have at least a secondary research area. So teaching, training of research students is really the basis of creating your primary knowledge, and on the basis of your publications, some of them you could have come with them from your own PhD. On the basis of that, you get your initial funding, and when you do well, it just snowballs. Money is always available for good research.
For excellence,
yes. Money is always available for good research.
Yes, fantastic. I think you broke that down really, really well. Thank you very much for that. Fantastic advice. And finally, on this section of our interview, are there any interests or perhaps hobbies that have contributed to your professional or personal life in unexpected ways that you'd like to share with us?
Problem. I enjoy sports. So many times when my either through teaching or research, if I think the researchers are struggling, I always ask them if they do any sports. And because I don't think sports is by any means the only example, but there are many parallels between research or education in general. That if you want to be successful in anything, you must practice. You must give it priority. So so I played a lot of sports as a young person.
I see.
And I enjoy following sports, and I think it's really influenced also how I do my research. And
fantastic. Which sport is it? Is it football?
As a boy, I played hockey. Actually, as a boy, I played a lot of football. But I was a small boy when I went to high school.
I see.
So in primary school, I played football. When I went to high school, I played hockey up to university.
I see.
And after university, I played a little bit for a semi-professional team in Nairobi.
I see.
And then it was academia. But I have a family, and all my kids have played sports. My kids they played a lot of tennis in this country, in Scotland.
Very nice.
It's been an interesting hobby, but it's very complementary to what I do in terms of research and teaching.
Fantastic. And it's healthy as well, isn't it?
Yeah, indeed.
It's a nice way to keep fit and everything.
Indeed.
Wow, fantastic. Yeah. Well, the time has come for our music break, and we're going to listen to a track by Tana Musica, Lovely, and we'll be right back.
Give it up for my baby. Stand innovation, baby.
This is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. And of course, we would like to take this opportunity to shout out to our sponsors, the Institute of Physics Scotland, and also the University of Glasgow, where I work, and the EPSRC, UKRI as well. And of course, our show, the Science Show, is something that's available to listen to live on DAB. You can also listen and watch us live at the website jamboradio.co.uk, and also via our YouTube channel, where episodes are uploaded on a regular basis. So that brings us back to our discussion with Professor Wasige. So just a couple of more questions to get to know you that a little bit better. So we know that your field of research is high frequency electronics. Would you like to explain to us what that entails, what it means?
Yeah, high frequency electronics. At the heart of this is the transistor, which we said was just a switch. That's what it is. And you can add a control electrode or a control terminal, and it can do amplification as well. High frequency electronics to how fast it can do these operations.
I see.
It's really related to how fast it can do these operations. DAB digital radio, I'm not so sure, because it goes via internet, it's software-based radio. But many people will be familiar with FM radio.
Yes.
So FM radio, they work between around 80 and 110 megahertz. Everyone is familiar with Wi-Fi. Wi-Fi, you go up in frequency to about 2.4 gigahertz.
Yes.
And high frequency electronics, it covers, people are familiar with microwave ovens.
Yes.
For example, every home has a microwave oven.
Yep.
So this works also in the 2 gigahertz range, but it's for cooking food. But when you make your for mobile phones, they work at 900 megahertz and double that frequency.
Yes.
So high frequency electronics is applications which start in the hundreds of megahertz frequency.
Yep.
So radio stations, so FM, TV is about 500 megahertz. Then you go to Wi-Fi. Modern cars, actually since the 1990s, you would have cars with the automatic braking. Automatic braking, if you approached another country for whatever reason, it would do this. So this would use radar, which operated in the 77 gigahertz range. So when we go up in frequency, we get new applications. Actually, when you go through Glasgow Airport or any airport today, you go through the screening.
Yes.
This is also a very interesting application for high frequency electronics. So actually at Glasgow, I think the system is from Rodan Schwartz, and when you go through, it takes an image of you to see whether you have anything on you, and this happens also in the 77 gigahertz range. So the area of high-frequency electronics is a specialist area. The applications are wireless communications. So this includes Wi-Fi, our mobile communications. Then we have security applications. And specifically for my research, we are interested, people in this country will be familiar with 5G. We'll be familiar with 6G. So the 5G was rolled out just before COVID. So now in Glasgow, in several places we have 5G. So that means you have really wireless connection via internet to the rest of the world.
Yeah.
And 6G will give us even more. And so my research is really to develop devices that enable this. For 6G, for example, a very interesting application is that what at the heart of this is that you can be able to transmit a lot of information within a second. The current Wi-Fi will do in millions of units of information per second. For 6G, the idea will be to reach terahertz. That's a trillion units of information per second. So and when you do that, what it opens up completely new areas of the economy. For example, one of the major goals is that a surgeon in London could operate on a patient in Glasgow. And to be able to do that, the communication between the distant places has to be done in real time. And that may not be possible today because of the delay. So, but with if we go up in frequency, we're able to shuffle information about the scene almost in real time. And so my research is about making these switches or these transistors, which are fast. Either transistors or the sisters, equally important devices are called diodes. Both of them really work in the same way. The way you implement the circuit's a bit different, but they do exactly the same thing. So the higher the frequency you can operate at, the faster, the more information you can shuffle between any 2 points. And so that's what we're doing. And when this is possible, then new applications come up, but we're always faced with the same challenges.
Yeah.
Energy efficiency today is a major challenge that you may be able to do this, but if you're using a lot of energy, then it's not so interesting.
Yeah.
So sorry for a very long answer.
Thank you.
But
It's packed full of gems. A lot of the questions I was going to ask were actually answered in that explanation. So we've seen areas of application of the technology. We've seen how it can, touch our lives in various ways. So that's really, really good. Very nicely broken down for us. Thank you so much. The other thing I wanted to ask about is neuromorphic sort of chips, nanophotonic chips, for example.
Yes.
Could you just say a little bit about that? Like, you gave us an idea as to neuromorphic has something to do with, sort of mimicking how our senses, how...
just like all areas of research, we always want to do things which are efficient, which don't use too much resources, which should not harm the environment, which are friendly to all of us. So in terms of computing, the computing we have today can do almost everything. But certain tasks like facial recognition or recognition of number plates, we can already do that. Or with AI data, we have a lot of data, and out of this we can process to find out what it tells us.
Yes.
And so the traditional computing, while we can do this, actually there's some problems if we try to do it just takes too long or takes too much energy. So neuromorphic computing is a new area that addresses this problem, that it actually has the transistor at the heart of it, just the way you call it a snapdragon transistor. But what's new about either transistor or other devices is a device called a memristor. And other devices like we did on our E project. But at the heart of it is you want this processing not to be energy intensive.
Yes.
And the biological systems are the most efficient systems that we know.
Yeah.
And they're that efficient because we know that the processing and the storage, the memory and the processing of information is integrated. So the new class of semiconductor devices being developed to be able to process lots of information, deal with lots of data. Neuromorphic computing is just a new type of computing where the main goal is to reduce the resources required to do the computation. So this means that we actually want to change the hardware. The present hardware, I think we can, but by changing the type of transistor, so the switch, we introduce some intelligence to the switch so that we can do this much more easily.
That's wonderful. Fantastic. So that brings us to the question for the week.
Yes.
And how will next generation semiconductors transform our world? You've kind of hinted to the answer to this question in some of your comments, but let's home in on that a little bit more. So in your view, what would you say are the most significant changes we can expect to see, say, in consumer electronics, or maybe even communication technologies as a result of these new types of semiconductor devices?
So autonomous driving.
Yes.
So this is already happening on small scale in large warehouses. Where the trucks move around goods from one area to another without a human being at the wheel. So actually, for actual cars in the US where it doesn't rain much, this is in the east of the US. There are already trials of this. In Europe, in the UK, autonomous driving is a big goal. So that when you go out, you can have a taxi outside and there's no driver inside, but it will take you where you're going. And for this to happen, semiconductors and actual semiconductors for communications, which enable, because the car it needs to have the capability to sense the environment just the way you would as a driver.
Like
So it needs to map the road, the surroundings, and be able to and so we need the semiconductors will enable new type of communication, and this communication, what's characteristic of it is it's a lot of data.
Yes.
So it's units, trillions and trillions of information to be processed very quickly. So the next generation of semiconductors will enable autonomous driving.
Yep.
And this will happen probably over the next decade. As I mentioned, in the medical field, you can have an expert in Glasgow does not have to travel to London to do an operation there or anywhere in the world because of also just same as for autonomous driving. It's about mapping the scene. There's lots of information which needs to be transmitted very quickly. And so the semiconductors are quite important. These are the hardware. But other than the hardware, clearly, for the hardware, the soul of this hardware is the software. So you need all the software to run around this. So
drive
autonomous, so driverless cars,
remote surgery,
future factories. So the way all these gadgets will be manufactured in the future will be more efficient, because in a factory there'll be human beings, but there'll also be robots. So actually the robotic world will probably transform, because each robot may have as much intelligence or even more than a human being. So it knows about its environment. It can work 24/7
and work fast.
It can work fast. Indeed, and so the semiconductors, together with communications, will enable this, and so that's the future economy. So
fantastic, really a lot to, so much to look forward to. I think it's really exciting to see
for sure
what things will look like in a decade or so if this system continues. Anyway, so that brings us to pretty much the end of our discussion. We could go on and on. There's so much we could talk about. It's a really exciting topic, electronics and semiconductors, because it's all around us, isn't it? Every aspect of our lives. And so with developments in these areas, things will change. The way we do things, the things that are possible will change as well. So really, really exciting. Anyway, this is the Science Show on Jambo Radio with Dr. Dada, and we're broadcasting live from Glasgow, and we've been having a very interesting discussion with Professor Edward Wasige. Before we go today, we're going to share a few science jokes.
As ready as I can be.
So today I'm not going to ask you to come up with jokes. I'll just share a few, and we'll see if we can unpack these jokes and see why, if they are funny, why they are funny. So the first one here says, why was the semiconductor a great party host? Can you guess what the answer to that might be? Just playing on the idea of a semiconductor. Why was it a great party host? It says, because it always has free holes and knew how to conduct itself.
I couldn't agree more.
Yes.
I couldn't agree more.
It's a bit of a play on words and the technical details about semiconductors. Okay, another one. What's an electronics engineer's favorite type of chips? This one is easy, probably.
Silicon.
Yes, you could say.
Not potato.
I would say microchips.
Microchips, yeah.
But of course, silicon is made of silicon, of course. Yes. What about this one? Why was the transistor so humble?
Yeah, because no one guessed it could do so much.
Yes, that's correct. I agree with that. But it's really tied to what you said before. It says, because it knew it wasn't the main component, it just amplified the talent of others.
Which is true.
Which is true. Yes, indeed.
Which is true.
Another one. How did the electron professor scold the naughty electron?
How did the professor score the
How?
naughty electron?
This is a bit of a trick one. The answer is, I got my eye on you. So just playing again on ion being charged with an extra electron and so on, or a deficient electron. Anyway, why did the semiconductor go to the doctor? This one is
to get doping.
Yes, exactly.
Wow, at least I got one. Yes.
Fantastic. Anyway, well, that's a wrap on this week's exploration into the fascinating world of science through electronics, semiconductors, and whether you're an avid enthusiast and wanting to keep up with the latest breakthroughs and impact on daily life from science and STEM in general, this is the place to be on the Science Show with Dr. Dada. And we encourage you to reach out to us through our social media channels and through email, info@jamboradio.co.uk, and don't forget to check our homepage on jamboradioscotland.co.uk/The Science Show for updates on our show. And to conclude this show, we'd like to, of course, thank our production team, Baron Utoekong Umoren, our producer, and we'd like to once again thank Professor Wasige for being on the show today.
Thank you very much for having me.
So, to play us out, we're going to actually listen to a song that I really like. It's by RJ Kniera, and it is Tia. And until next week, we'd like to say, stay curious.